Hello. Here we'll have a couple of calculations of determinants of matrices where not all entries are numbers. So there will be some undetermined thing, a parameter. That will be important for applications of determinants, for finding eigenvalues of linear operators. But right now it's just a problem of computing the determinant of a matrix, say this 3 by 3 matrix, where we have numbers, but also we have this unknown t. So let me complete the matrix, something like that. And one question about that determinant would be just find all values of t for which this determinant is 0. So let's compute the determinant. We could look at it formally as a matrices with coefficients and polynomials of t. So some polynomials are just constant terms, some are not, and then we just know that the determinant is a sum of some products, and if entries are polynomials, so will be the determinant. So we're just computing this polynomial answer. And in this case, when we cannot really divide at our will, even if a polynomial is non-zero, dividing, we will have to assume that the polynomial doesn't vanish. So that's a big assumption. Division is an important step in Gauss elimination process. So Gauss algorithm is not that applicable in the case, but other two ways of computing determinants, like using the formula for 3 by 3 case, it's still very effective, or expanding along a column or a row, they are still good. So I will first use the formula to find the determinant, and I will start with listing all products with sign plus. It will be diagonal product, which will give you 1 minus t cubed. It will be product of these 3 copies of 1 coming with sign plus, and there will be the product of these 3 negative ones, and that will be negative 1. And that is always a positive sign, and the rest is negative sign, and that will be this product. Well, because one of the factors is negative 1, I could just write it as 1 minus t. And then it will be the product of these 3 terms, and again I have the same answer, so I have it twice. And finally the product of these 3 terms, which is the same product. So I have 3 copies of 1 minus t coming with sign minus, but the answer, total answer is plus 3 1 minus t because of these minus signs in the products. And these two ones cancel each other, so we are left with 1 minus t cubed, and then 1 minus t 3 times. We can factor 1 minus t immediately, and we'll have 1 minus t squared plus 3. And factoring is important. As soon as we can do it, we should, because if we want to find all values of t for which the determinant is 0, we will need to find the roots of the answer of this polynomial form of the determinant, and finding roots are easier when polynomials are smaller degree, and really roots are just complete factorization when we find them all. So factoring on the way is, if it's possible, it's the thing to do. What is left in this factorization, the second factor is quadratic, so let's write it as it is. T squared is the highest power, then we have negative 2t, and the free term from here is 1, and then 3 on top, so that is the quadratic polynomial we have. Finally, answering the questions, what are the values of t making determinant 0? We have the first root from the first factor. Or we have two roots of this quadratic, so let's finish this problem by finding the roots of this quadratic. The formula for the roots is the following. So we have linear coefficient with negative sign plus or minus the square root of what is called the discriminant, halved, because the leading coefficient is 1. And the discriminant, the thing under the root, is the square of this minus 4 times the free coefficient. So the square of this is 4, and then minus 4 times 4 is negative 16. So subtracting 16 out of 4, the result will be negative 12. And assuming that we are dealing with real numbers, that is nonsense. There is no meaning for that, so there will be only one real root. But if we are willing to extend our numbers to complex numbers, then yes, and there will be 2 more roots in complex numbers that can be rewritten as taking 4 out, taking it from under the square root, turning it into 2, and then cancelling out. We'll have 1 plus or minus. Then we'll be left with negative 3 square root of, and that is the same thing as I times square root of 3. So I is this notation for one of square roots of negative 1. I is the new number where 2 real numbers which solves this equation. And that is not really video when we deal with complex numbers as such, but this is just computing the determinant with a parameter. So let me check my answer by computing this same determinant differently. This time I will use row expansion to find the answer. And all rows are equally bad or equally good, so I will just take the first one. And expanding in the first row, I will start with the first entry, and then the cofactor for that will be the determinant of that 2 by 2 matrix, these 4 numbers, with sign plus. Then to account for signs of cofactors, we can just follow the simple rule. If we start from one term where we know the sign, the next sign will be the opposite. So we'll have negative sign for the cofactor of this entry, and that is just 1, so I'm not writing it. The minor for that element will be the matrix with these 4 entries. So it will be negative 1, 1, 1, and then 1 minus t. The next term will have cofactor sign plus, but the element itself is negative, so that's what gives this minus sign, and then the minor is this matrix, the corner matrix, and the determinant of it is what I should write here. The rest is computing 3 determinants of size 2. And this one is the product of 1 minus t with itself, minus the product of these off-diagonal entries, which happens to be plus 1. The determinant here is negative 1 minus t, and then negative 1 on top. And this determinant is negative, negative, positive 1, and then with negative sign 1 minus t. So collecting the terms, what I should see is positive 1 minus t coming from here, positive 1 minus t coming from here, and that would make 2 copies of 1 minus t on top of 1 copy of 1 minus t coming from this product. So factorizing again, I'll have what I had in this term of the expansion plus 2 more copies of 1 minus t, so that will be 2 more on top of 1, it will be 3. And what is left is negative 1, which is positive 1, and then negative 1, which do cancel each other. So these answers agree, meaning that the first computation was correct. Let me do another problem of similar nature, computing the determinant of a matrix with a parameter, but this time make it larger, 4 by 4. But I will make it larger still to be able to compute it in the remaining space. I will make it somewhat nice. So something like what makes it nice is this block of zeros. So something like that. What happens when we compute such determinants? Let me draw a general shape of a matrix where we can do the same thing. So what is crucial is that we have block structure in the matrix, and we have 2 square blocks located on sort of the diagonal of this 2 by 2 blockish structure. And then below or above, we have a block of zeros. So these are square, like we have here, and this block is full of zeros. Then what happens, no matter what A, B, and C are, the determinant of the big matrix is always the product of determinants. And the reason for that, just the definition of the determinant, it's this slogany form which makes it easier to see that we have to take products of matrix entries, computing this determinant, sitting in different rows and different columns. And if we look at what we can take from last bunch of rows, just passing through this zero block, they will all have to be taken. To get non-zero answers, we'll have to take entries sitting in B. And effectively, we will be just computing the determinant of B. And then the B columns will be forbidden to use, and we will be left only with A columns. So then kind of like switching between the rows and columns. The rest of the non-zero contributions to the determinant will have to only use the first columns, the columns of A. And that will be effectively the determinant of A. That will be just the determinant of A. So that's how this rule comes from the definition. And now putting it to use here, we can get a very quick answer. So it doesn't matter what happens above in this diagonal diagonal block. It's only the off-diagonal block. It's only the diagonal blocks which contribute to the determinant, and each of them is a quadratic expression in well, it's a polynomial expression now unknown t, quadratic in the first case, -1 plus t, and linear in the second, t minus 2 plus t squared. I forgot to write it here. And so the factorization is easy because the first factor is t minus 1, which factorizes into t squared minus 1 rather. It factorizes into t minus 1 and t plus 1, and the second is t minus 2. So the roots of this polynomial, which is our determinant, are 1, -1, first 1 and 2, for which for these values of t, the matrix will become degenerate. Its determinant will be 0. For the rest of values of t, the determinant will be non-zero, just because it has this shape. That was it. See you later.